Today, we're talking about polymerization. Now, that might sound complicated, but it's the chemical process behind almost everything around us: plastics, fibers, adhesives, all the stuff that basically builds our modern world. And it's a process that's always walking the super fine line between incredible creation and, well, total chaos.
So think about this for a second. How on earth do you control a chemical reaction that just wants to run wild, getting hotter and hotter until it could, actually explode?
And then, how do you take that same raw, explosive power and tame it so precisely that you can use it to build the world we live in? That right there, that's the central puzzle and the absolute genius of polymer chemistry. So let's get into it. All right, first things first. Before we can talk about controlling the reaction, we need to know what we're even trying to make. What exactly is a polymer? Honestly, it's way simpler than it sounds. Just imagine you have a giant box full of individual paper clips. Each one of those paper clips is what we call a monomer. Polymerization is just the act of linking thousands or even millions of those clips together to make one incredibly long, really strong chain. And that chain, that's your polymer. So if that's the goal, just linking paper clips together, what's the most straightforward way to do it? Let's take a look at the first, most obvious approach that chemists came up with. It's called bulk polymerization, and it is beautifully, elegantly simple. You just take your liquid monomers, your paper clips, toss in a tiny bit of a chemical starter called an initiator. Think of it like the first domino that gets the whole chain reaction going, and then you add some energy, usually heat. That's literally it. And you know what? The results are amazing. The process is simple, and because you haven't added any extra junk, like solvents, the polymer you get is incredibly pure. It sounds like the perfect method, right? Well, not so fast. Yeah, there's a catch. A big one. This wonderfully simple method has a really nasty habit of, going wrong in a very spectacular, very explosive way. So here's what happens. As those polymer chains start forming, the whole mixture gets really thick and gooey, kind of like honey or syrup. And that thick goo is a terrible conductor of heat. It traps all the energy from the reaction inside, which makes the temperature skyrocket, which makes the reaction go even faster, and you get this dangerous feedback loop called autoacceleration. So, okay, clearly the just mix it and hope for the best approach wasn't going to cut it for every situation. Chemists needed a smarter way to get all that heat out. They needed a safety valve. And the big breakthrough idea was just add a liquid, something inert, like a solvent or even just water. This liquid doesn't actually participate in the reaction itself. It's just there to act like a coolant in a car engine, soaking up all that dangerous excess heat and keeping the whole system stable. This one idea changed everything. And this led to two major techniques. The first is suspension. You just whip up the monomer in water and it breaks up into tiny little droplets. Each one of those droplets becomes its own tiny little reaction vessel, safely cooled by the water around it. The other method, emulsion, is even more clever. Here, the monomer is hidden inside these microscopic cages called micelles before it's put in the water. This gives you an incredible amount of control. And you can see exactly how that works here. Those surfactant molecules, which are basically just soap, automatically form these little spheres in water called micelles. They act like tiny protective lifeboats, safely carrying the monomer on the inside. The reaction happens inside that tiny protected space, all while being cooled by the water outside. It's an absolutely brilliant solution. So let's see what this looks like in the real world. This is an industrial flow sheet for making a type of acrylic using suspension polymerization. You can see the core idea right here. The monomer and the water are mixed to create those tiny, cooled droplets. From there, it all goes into a huge reactor where the magic happens, and then it's filtered and dried to get the final powder. It just shows you how a simple lab idea gets scaled up into a massive engineering process. But the chemist's toolkit doesn't stop there. For really specific materials, they've come up with even more specialized, almost surgical techniques. This one is my absolute favorite: interfacial condensation. Okay, so you take two different monomers and you dissolve each one in a liquid that won't mix. Think oil and water. Right where those two liquids touch, at the interface, they react instantly to form a solid film of polymer. You can actually grab that film with a pair of tweezers and just pull it out as a continuous thread. It's called the nylon rope trick, and it is so cool to watch. And there are plenty of others for unique situations. If your starting monomer is a gas, you can use gas phase polymerization. If it's a solid crystal, you use solid phase. The point is, there is a custom-built technique for almost any kind of material you can imagine. So, with all these different options on the table, how does a chemical engineer actually decide which recipe to use for the job? Well, like with most things in engineering, it all comes down to trade-offs. And this table really lays it out. You can see the pattern, right? You're almost always trading purity for safety and control. The simplest method, bulk, gets you that super pure product, but as we saw, it's dangerous. The most complex method, emulsion, gives you amazing heat control, but you're left with a less pure product. It's always a balancing act. And here you can see how those choices lead to the products we use every single day. Strong fibers like nylon 6 often need that high purity, so they're made with the bulk method. The PVC in your pipes and window frames, that's made using the much safer suspension method. And all the latex and paints and adhesives, that's made using the highly controlled emulsion technique. So the next time you pick up your phone, or really any plastic object, take a second and really look at it. Think about its properties. Is it perfectly clear? Is it super strong and durable? Because now that you know the different recipes, you can start to make an educated guess about how it was made. And you can appreciate the incredible chemistry it takes to tame a runaway chain reaction and build our entire world one molecule at a time.